the next our lecture on embedded systems. Okay, so today topic we will discuss about operating system and operating system related to the sequential systems, and more than it's related to the preemptive systems. But let's see what about is that. First of all, let's see what an operating system is. Okay, usually I ask you to answer that, but according to the general definition of an operating system is a system that is managing the resources of let's say computer system, let's say like this. Yeah. And usually it is managing the memory, peripheral, and the processing time. How? Let's imagine first of all that we want to assign to an external pin, or let's switch on an LED, but not switch on LED, but we have a status on in a variable. That means we have memory, and we say that okay, the digital read, digital write to pin 1, the value that is contained in the variable B. And in this case, we have memory because we have a variable A that is somehow allocated. Some system allocated that, but this some system is a memory manager. We have some peripheral drivers that in our case is digital write. Yeah. And we have the assignment operation. That means that we are using some, let's say, operation to make this happen. Okay, so in this case, with 2 lines of code, defining that A equal to 1, let's say, and digital write to pin 1, the value of that is contained in A. In this case, we used all the resources. That means processing time, peripheral units, and memory. So, okay, and classical programming, we say that okay, we are writing some programs that is usually in the function main and so on. Yes and no, but usually taking in consideration that this application is running on some platform, let's say on personal computer. In this case, when we define the variable A, we asking the kernel or I don't know, the core to allocate some memory. We access some drivers that are in the systems, and of course it is somehow somewhere is asking the peripheral for permission to write, because behind of the driver usually we have some mechanism, some management system that are allowing or not to access the peripheral models, let's say the monitor. Okay, and usually when we are performing this operation, more than in case of a complex operating system like Windows or Linux, usually we are staying in a queue when the kernel will select our application for execution. Yeah, and in this case, operating system is responsible to manage or all the management system usually are behind the operating system and usually are accessible via the, let's say, kernel or some scheduler or I don't know, management system. So we have application on the upper layer, and usually they have some libraries, special libraries like malloc, let's say, for memory allocation, for dynamic memory allocation. And we have digital read, digital write, serial read, serial write. Yeah, and in certain situation we can have some situation when the when the serial is busy with another process, and in this case we will need to manage the access to make some arbitration. Yeah? And that is what an operating system usually does. Yeah, but let's start from the classical programming. Yeah, just a quick question. I want to raise the hand who tried some simple application like reading a button. Yeah, and switch on or off an LED. Okay, thank you for all. Okay, others. Nice, nice. Okay, I see that you are more or less familiar with Arduino programming. Yes, we are using some Arduino libraries in our case, and usually we are thinking about the programming on Arduino like, okay, everything we are putting in a function setup or loop. Yeah, setup for that will be executed at the begin, and the loop that is and the repetitive cycle. But let's see differently. Yeah, let's see that we have usually as a system this main function is a transfer function or the functionality that is defined here. But let's see from by definition what is a system. A system is a collection of components that are participating, let's say, on solving a problem. And our problem, when pressing a button, we are toggle an LED. And in this case, we can say, okay, we can separate this problem in three components: one for acquisition or sensing, another for evaluation, and the second part, the last part, is the actuating. Yeah, we are actuating some and lighting by the LED. So in this case, the question is, and please, for a quick question, just answer. When who is doing the resource management, or where we are doing resource management, and which, let's say, functionality or component, or let's say like this. So meanwhile, I know that there are some delays on the messaging, but the right question, right answer is everything we are doing in the inside of the function main. That means this transfer function or the functionality of the system. In our case, for this simple application, is the function main. Okay, usually, not usually, but always, this functionality and the function main, it doesn't matter on which operating system or which platform, but usually it is usually we have a kind of power on reset interruption. Yeah, when we are switching on, we have power on. After that, the power on is generating the reset, and reset is calling, in our case, the function main. So in our case, this function main is interrupt service routine for function for event reset. Yeah. Okay. What I can say that as it is now for the Arduino, yeah, for the Arduino board, because this name is more popular among you. Yeah. Even in the Windows system or Linux system, for the Linux and for the Windows, we will have the function main, and that will be automatically, or we will have a hardware call for this function on the interrupt service routine generated by the hardware event reset. So this means that Linux has its own main function, and the name of the function, surprisingly, but is also main. And in the Linux and in the Windows is the same. But now how it was built upon it is a different question. But we know that every microprocessor or microcontroller is starting from a main function that is considered as an entry point to the operation. Yeah, now in our case, we are managing resources, okay, by those three components inside of the function main. So we can say that in our case, we have a minimal single process operating system, yeah, that is operating inside of this infinite loop. So the question, is the main function an operating system? In our case, yes, it is a minimal operating system because we have here, let's say like this, but let's go further. Yeah? Okay. We have here the initialization of the peripheral. Yeah? We have some, we will see in one of the next slide, the details, but now let's imagine like this. But most probably you're not familiar with, by the way, just raise your hand who is familiar with microcontroller programming without Arduino. Just raise your hand. Okay, nobody. But it's nothing special because the difference programming with Arduino or without, when you are programming with Arduino, you are staying on your own to define this main function. In Arduino, it is already defined, and we have here a kind of this. Let's do like this. We have this setup called here immediately after the main, yeah? And the loop is something that is invoked or it's called from inside of an infinite loop. So the Arduino.h is including this functionality. It's a kind of защита от дурака, because usually beginners doesn't know what means to program a microcontroller in C, and they need some kind of simpler methods. So in this case, they defined, the Arduino defined the function setup, where they say that, okay, everything that you want to start from the begin, from the power on, you put inside of it, and everything you want to be executed in a loop, put in the loop. But actually, we will have a function main, yeah, that by in the begin it's calling the setup function, and in the loop it's calling the loop function. This is exactly. So now after we will, in case we use the setup and loop system, this is the content of the loop, yeah? And this one is the content of the setup. So when we are writing programs with Arduino, you just have some additional layer of call functions. Yeah? Now, just a quick question: if you understand or not, or the level of your understanding from 0 to 10, what means to program, and what is the difference to program directly to the microcontroller, and what means to work via Arduino. Okay, thank you, Mihai. Others? Nothing special, but everything else like digital read, digital write, this is just some libraries. You can use that, you can choose to not use them. You can access directly the peripheral and everything else according to C standard. Yeah, nothing special. Just in main we are calling the setup. Arduino is calling the setup, and in the infinite loop is calling the loop. Nothing special. Thank you for who is providing feedback, because I want to see that you are on another side of the this TV. So, but let's go to our operating system, and today we will build an operating system, or okay, an preemptive operating system, on sequential operating system. Okay, so now let's try from this. Usually when we are writing some program, some application on the microcontroller, we will have a main function, main function where we will go to define something on an infinite loop. Why infinite loop? Because let's imagine like this. What if this main function will finish? In this case, we'll have to exit somewhere. But where? Because we entered to the application by the main function. Okay, we entered by the main function. We execute it. And let's imagine we don't have this infinite loop. Yeah? Where is the return? Where we are going after? Nowhere. But let's imagine that we are going somewhere in a region of program memory where something is defined. And let's say that this one is pressing a red button, let's say launch some weapon or I don't know, a red button. Okay, but we will say, okay, but I didn't define this function. Yes, you didn't, but this line of code somehow can be related to activate a pin that is connected to this button, let's say by a joke, but who knows? Because we don't know, because this code, it's a random code that can be located in the memory. In this case, we should keep under control, the processing under control. This is why we have the infinite loop here, because we want to bring back the processing under our control and to not have execution somewhere in the, I don't know, a random area. Yeah. So now, please let me have. Just from 0 to 10, if you understand the idea of the infinite loop, why we need an infinite loop in the microcontroller programming. Okay, meanwhile, you are giving me feedback, I will comment, we need that to keep the processing under our control or under our application control. Okay, thank you who provided feedback. It's not too late to provide again if you understand the idea, but I need your feedback. Let's go further, because this is just a small introduction to microcontroller programming. Nothing different to the real C programming, except we have some specific driver function like digital read, digital write that are accessing the peripheral models, but everything else, it's according to general rules of programming in C language. But let's see, because according to the system, okay, when we are focusing on the programming, we are focusing on the, let's say, instruction and function and so on, yeah, but we are developing system, and usually a system, let's say an embedded system, has different components with different proposal. And in our case, let's say that this we will define according to the general architecture of an embedded system. We will try to define some, we'll have some actuators, yeah, here. We'll have some sensors here. We'll have here some power management. Yeah, we'll have some communication, and also here we'll have some, let's say, user interaction maybe here. So sensor, actuator, COM, user interaction, database. Maybe we'll have some data structure here in the application, and here we'll have the app. Yeah, and now we redefine it. Okay, this is the general proposal, general architecture of an embedded system, but here we have the specific, let's say, to a robot. Now we'll have some components that are responsible for sensing, for actuating, for control in the application, yeah, and communication, of course, user interaction. Now we say, okay, but every component has its own life, and it could be defined as a special task or a special application that are working. Okay, it's a special work. Okay, what is actuating? This is the explanation. Sensing it when we are gathering the information from outside, yeah, and converting the physical value or physical change to the information. So pi to info. And actuator is vice versa, converting the information to the physical change. Now, more clear? Anastasia?
I'd say a 9.
What?
I understood the idea. Anyway.
Okay, thank you. We'll have a special chapter for everyone. Okay, now, but let's say that every component has its own processing time, and we are developing the sensing apart in a special task. The application is apart in a special task, and the actuating a special task. Okay, now according to our understanding of an operating system like Windows is or Linux, we will have 3 different tasks: 1, 2, 3, sensing, control, actuating, and those tasks we can imagine that, okay, according to the operating system we see, and even here, let's see, yeah, we see that we have a lot of let's go in details. We have a lot of application that is running in parallel, and we see we have some mouse, we have this presentation, we have the pointer that is running on the screen, and so on, different application. And seems that the computer is it's managing everything without any delay. And from our understanding or from our own feeling is that we have all those tasks that are running in parallel, and we can imagine, okay, but okay, one processor can manage one single task. Now, it doesn't mean that we have, okay, in case of dual core, we can have 2 tasks and so on, but it's not like this, because it's somehow managing the processing time that it succeeds to manage many tasks in parallel without having some lags or some delays for everyone. But let's see how we do that. And today lecture we will see how it is done by sequential system, yeah, or preemptive system. Preemptive system means when a task is releasing the processor by its own without interruption. Okay, but let's see. So now we say we have 3 tasks, and usually when we are defining, and now according to single process operating system, like, just raise your hand who knows, who did hear about the DOS. What is DOS? Yeah, DOS operating system, the first operating system that was proposed for the personal computer. Yeah, and this operating system was nothing special. It was just a function mine with some scanf, printf system that is usually it were waiting for was waiting for some inputs, scanning it, decoding it, and calling the specific file, let's say, from the database or from the disk, yeah, disk operating system, and transferring the control to it. That means we have some. Now, when we are here, we'll say here we are in the operating system. Now we have a call, let's say, introduced some command, and the control is transferred to the task A. That means during the task A, operating system doesn't have access to the system. Why? Because the control, the system is under control of the task A. So until it will finish its job, we will not have access. Okay, the operating system will not even run. It will wait until the return, and after this will return, we'll have back the control to the operating system. Now we would like to have a single task operating system, and we would like to have some multitasking. Okay, no problem. In this case, we'll say, okay, we'll do some sensing, let's say, control, another task, and we'll make some actuating. Yeah, let's say In this case, we will sense the button. We will decide the value of the LED. After that, we will update the value of the LED by another task. So instead of having this description, we will break it in 3 parts, let's say, yeah, and we will define it as different tasks. Okay, sensing, control, actuating, and we'll provide information, let's say, from one task to another task somehow, like it's here. Yeah. So this is generating the status of the LED. The control is getting the status of LED, generating the status, another variable, let's say, status for LED. Yeah? And the LED is updating the status to the, let's say, output pin. Yeah. So we'll have 3 tasks. So this task will be split in 3. Okay. So now, what that means? That means the operating system, okay, the OS, that is actually our main loop, yeah, is calling the task A. Task A is finishing its job, giving control back to the operating system. After that, transfer the control to the task B. Task B is doing his job, giving back the control to the operating system. Yeah. And after that, operating system, okay, the while this infinite loop is giving the control to the LED task, yeah, and it is finishing its job. So it's finishing. So we'll have a kind of cycle, an operating system cycle now. Okay, the loop cycle we finished, and we finished everything. So we start from the beginning. Yeah. In our case, we will have a kind of CPU load about 100%. It's similar like this. We have here the idle process that now in our case is about 81%. That means in this case, it's the CPU load is about, let's say for the 75, we have 25 percentage of the CPU load. What that means? That means that applications are running 25% of time on the operating system, on the kernel. Yeah. In our case here, this application will have like always, that means 100% of the time, the operating system is giving the time, processing time to the task. Yeah. So this is the first approach. What we did from here, we split and we show how we can run 3 tasks in parallel. Yeah. And now we will have a kind of zoom out to this timeline. We'll have something like this: one application, the second application that is running in parallel, and third application. Zooming out, we'll have something like this. Yes, we have first task that is reading the status of the button. Yeah. The second is controlling, that means deciding what will be the status of the LED. And the third task, let's say, it's updating the status, the pin status, let's say like this. Yeah. So this is just a kind of zoom in, and we see that we have this approach, and this is, let's say, first try to make this simple application in different tasks and to run many tasks in parallel. So now single process, okay. And please give me the feedback, the level of understanding of this approach, how we are doing parallel programming or parallel processing in an infinite loop. So we'll try to step by step to build, and in order to have an sequential operating system that is usually used on the real-time application on the embedded systems. Okay, thank you. I see that some of you already understood the idea. Let's go further. but I want more feedback. I want to everybody to be involved in order to see that the real status, because I don't have to have interaction only with the people that understand me. I want also to have interaction with people that don't really understand what we are speaking about here. So please, even you don't understand, don't be afraid. We don't record it on our video. I have it apart. Okay, next step. Let's see what can happen during our parallel processing. We can have situation that what we are doing. We are waiting for pressing the button, and only after we are going to process. So what that means? That means a certain point of the task, yeah, we'll have here a spin lock. What a spin lock means? Means to be blocked for a condition. Yeah, let's say while is button press is equal to false, so we are waiting here for button press. So in this case, being blocked on the first task, we will never reach the second task and even the third task. So that means in our case, in case we are using in our application spin lock, that means we can block everything that is that should be performed after that. Yeah, and in the Windows 3.1 or 3.0, let's say like this, it was the first version of the Windows 3.0 or maybe earlier. Yeah, it was just an application that was launched under the DOS operating system by the command, let's say, win.com. Yeah, you just launch it, and you'll have a kind of graphical application where you can go to browse the files and to make a double click. But from the moment you make a double click, you transfer the control to the application that you were clicked. After that, you cannot go back to the operating system, because you, even from this graphical interface, let's say first version of the Windows, you transfer the control to the task A. Now you don't have any access to except the interruption, okay, of course, but those are just details until the application let you back or give the control back to the operating system. It was how it was working. Now, in case of let's say blocking or freezing in one application, you were in a situation to reboot the computer because the application freezes. Yeah, because of one bad written application, everything crashes. Yeah, not crash, but okay, freeze. Now, in our case, we should take this in account, that we don't have to block the execution, because now in the our multitasking or preemptive operating system. Preemptive means when every application give back the control by its own. It's not interrupted. Windows is non-preemptive. Oh, okay. Okay. So, okay, this is not non-preemptive. Yeah, we cannot preempt it or interrupt the. This is non-preemptive. Yeah, the preemptive, that when we are the operating system can interrupt a task, even this is under control. So now doesn't matter at this point. So now we will have an task when we have the spin lock. So we have situation that the task B will never run until we will solve this condition. Now we should have another approach. We should rewrite the code in order to not have this spin lock. Never. Just, okay, try the condition. If not, then give back the control. And in this case, we will have a kind of situation. Execute here, nothing to do here, go this to the second task, nothing to do here, go to the next task. Yeah, so now let's do like this. So we will rewrite it this way, and we'll have like check, not block. Wait until pressed, but check if pressed. Not pressed, let's go to the next task. We'll see what the next task should perform. No spin lock there. No spin lock allowed in the application, in the real-time application, and so on. In this case, we will have a kind of fast execution of the cycle. So this loop cycle will be very, very fast. We will still keep the 100% CPU load, but we will not have problems and blocking on any applications. So everything will be done in parallel in real time, because the if else it's fast execution, and usually we don't have too much things to operate, and more than it, the processor usually is very fast, and even you have a very complex algorithm, usually it is doing very fast. Yeah, but we don't need so fast. I don't need to check on every microsecond the button. So I can say, let's have this loop cycle a little longer. Yeah, and we will put a delay here, let's say for 1 milliseconds. And in this case, our cycle, and we go to, let's say, sequential. We have sequences of execution for every 1 millisecond. Let's say 1 millisecond, recheck the system, update the outputs. 1 milliseconds, recheck the system, recheck the inputs, evaluate, update the outputs. And in this case, we'll have a kind of sequential system with a recurrent execution. So now, just a quick question. Let's see if you understand the how we proceed in order to remove the spin lock from the operating system in order to have parallel execution. Just the level of understanding from 0 to 10. So by this concept, forget in the embedded system to use while true or spin lock. The instruction while for embedded programmers doesn't exist. Never use, is forbidden. Never use this one. And now you should think to write application without while. Why? Because we will have problem when we would like to make some things in parallel. Why? We will stop everything. Why? Because we should release the execution to another task. Yeah. Once we will block here, everything will stop here until we will have this condition done. So we should rewrite our spin lock to transform them to checks. Nothing to check. Next time, after 1 millisecond, I will see it again, but never use it. Okay, thank you for the feedback. Let's go further, because we have another problem here. We still have 100% CPU load. Why? Because we are doing that, all the execution in the while true. Yeah, that means we are doing something. Yeah, doing something, and we have here a delay. And this delay is another kind of spin lock. But okay, it's not related to any task, and we can say it's related to the operating system. Yeah, but it's operating system time that is always is 1 millisecond. That is just providing us the same sequentiality, but not more. but we need more. We need to save this time for other different proposals. We will see how we will exclude even this delay from here without keeping blocked, because we will go to, inside the delay function. We will see there something like down counter that is counting down the value that you provide to the input. Okay, and when it will be done by the down counter will reach the 0, we will get out. Yeah, but we are doing something. We are counting down and doing nothing. So delay is not about not doing anything. It's about doing nothing. So we do something. Something that means nothing. Okay, but let's do a different approach. We can do differently. We can exclude everything from the while true, but play a little with the interrupt service routine. And now, what is that? What is an interrupt service routine or interruption? Interruption, it means to interrupt the normal execution for a high priority event. Yeah. So now what we can do? Every microcontroller has many peripheral models, and many of the I can say that almost all peripheral model have some hardware event that can provide some interruption. Now we can bind to this interruption an interruption service routine. That means in case we have interruption, we can call automatically an interruption service routine. So we will service this interruption. Now for the button, we can say we can set up an external interrupt service routine, and we will evaluate the button-led application, let's say the task A here. Now let's say we have to sense something, some sensor, some analog sensor. In this case, we can provide an analog digital converter interruption service routine, and that is converting always, finishing converting, it is generating an interruption, and we get the data, analyze it, and doing something in some task. Let's say we have some communication. Every time we receive a new chart via serial interface, the microcontroller will generate an interruption. Yeah. Okay. So we will process this new income from the serial interface by an interruption service routine. In this case, we can say that we can realize, we can perform the multitasking using event-driven approach or interruptions. So we'll have interruptions. Now let's see, because how often we are pressing a button? Once in a second, once in a minute, once in a day. So we only once in a day will launch this task and will use processing time. How often we are providing some message via serial interface? Once in a second, once in a minute, once in an hour, 10 times in a minute, but after that staying 1 hour and so on. Yeah, and that means we will use processing time only when receiving a new bytes from the serial interface. Okay, now here ADC, we can set up it to have once per milliseconds. I don't know how often, but we can set up it. And now we'll see. The execution of the microprocessor is very, 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 very fast. What that means? That means the almost all time it will stay in the infinite loop, in the idle, and only for few microseconds it will use the processor for the task A recurrently by ADC for few microseconds, and sometimes depends when we send some bytes to the serial, it will use, but almost of a kind of 99 and 99%, it will stay in the idle process. In this process that we have here, and you will see, here we have system idle process, that meaning not doing nothing, but even not doing anything. Yeah, we are not staying here in delay. We are staying on an infinite loop without doing anything, because here in delay, what we are doing? We are delaying, we are doing something. But here we will have situation, but this time is free for all the background process, and we can say that in the idle process we can put something. Okay, let's count the time that we are not doing nothing. Yeah, okay, and so on. So here we are, even maybe we can develop a system that is counting the CPU load. Usually it's done here. So this is multitasking, but it is very real time operating. Now it's real time. That means it can react immediately to the. Here we don't say that we are reacting immediately, because we are reacting once in a millisecond. Here we react immediately, but we are using processor on the 100%. Okay, we don't want to use the 100%. We put a delay because we don't need to check always, because usually changing meaning changes on the output, meaning to use some power on switching. Okay, we try to use that with event-driven and interruptions, but what we, in our case, we have to use for every input, we need to use one external interrupt. Okay, what if we need 100 buttons? Okay, one microcontroller can have one external interrupt, but not, we don't have so much interruptions or peripheral models as many tasks we have. So in this case, it's okay for small application, for very, very real time, but it's not good when we want to scale. Yeah, and usually when you port from one microcontroller to another, we have even to redefine everything according to the hardware of the next microcontroller. So now give me some feedback regarding the how the level of understanding how we are doing multitasking using interruptions. It's a different approach. We'll see by the way in the next practice session how we perform and how we manage interruptions in even via the Arduino, but it's just defining a function that we bind it to some events, interruption events, but need some feedback from you now about the level of understanding how we perform multitasking using event-driven. Meanwhile, I think you already have some experience in another courses using event-driven systems. Okay, started to have feedback. Thank you. Just define the interruption and the proper interruption, yeah, for every task. Because if task is working with analog interface, we'll need to set up the interrupt service routine for the ADC. It is usually built in the microcontroller. Yeah, USART also is built in, or serial is built in the microcontroller. Yeah, you don't need to write anything special, just bind some function, a function to a special event. Okay, thank you for the feedback, but let's mix something. We have interruption, we know that we have interruption system. We see that when we will transfer the functionality to the interruption, we will have a very low CPU load And in this case, we can use this saved CPU load for another application. Yeah, because here we see that we have only 3 tasks for the CPU load 100%. We see here that we use the same 3 tasks, but we saved 99.999, let's say, percent from the CPU load. But we need something alternative solution that is not using so much the hardware configuration and using some operating system approach regarding the how to manage the CPU time. Okay. So let's see the one of them. Let's say the main slide. What we are doing here. So now all those tasks that here we are doing in the infinite loop, yeah. Here we transferred it to the every task to its interruption, its appropriate interruption. But we will do something like this. We'll define an recurrent, let's say 1 milliseconds or let's say 10 millisecond timer interruption. Yeah. So timer interrupt. We'll configure the timer interruption on let's say 10 milliseconds, and we will have once in 10 milliseconds and wake up and transfer all the tasks that were here inside of this. So we'll have the same that we had previously. Yeah, and this in this case the main was the operating system and idle. Yeah. Now we will split it in two, and we will have the main as idle, yeah, and interrupt service routine, the timer 0 in our case, will be the operating system. Now the idle process will continuously, once in 10 milliseconds, will be interrupted. Yeah, and here we will go to execute this function, interrupt service routine. Now, this interrupt service routine will give the control to the first task, let's say without any spin lock. The task A give control back to the operating system, meaning to giving back the control to the interrupt service routine. After that, second task, third task, giving back the control to the interrupt service routine. Yeah, and now finishing everything, we will return back to the idle process. And here, really, we are not doing anything. We are staying here in the idle process. Here, we are staying in the idle process, where idle process function is doing nothing. So now we have a kind of CPU load less than 100%. In our case, let's say by this image, we'll have a kind of 60%. It's not real because, okay, we should go in details how many time it's take from the recurrency. Okay, we have this one system tick. Yeah, in our case, we select that system tick will be 10 milliseconds. Okay, most probably here we'll have some microseconds, but according to this image, we'll have 60% of the CPU load. Everything else, so that means we can use even many tasks in parallel to run. Yeah. So now, please, another feedback from you. The level of understanding how we proceed to do multitasking through the timer interruption. By the way, this is the topic of the second laboratory work. Yeah, we have to do nothing, so the loop function will remain empty, and everything that was in the loop is transferred to a special function that is binded to be is configured to be invoked by the once in 10 milliseconds. How we do that, we will see in the practice session. But we have something like this. Yeah, and the C code will have this one. No spin log, be attentive, because having spin log, that means we will block and we will remain here. Yeah, will remain here. So thank you. See a lot of feedback. Thank you for involving and waiting for others to be involved. So we have once in a 10 milliseconds, we call all the functions, but do we need so often to check the button once in 1 milliseconds or 1 in 10 milliseconds? Maybe yes, maybe not. We have to decide. But sometimes, according to the system, let's see what happens here. First of all, let's see here. Usually, we have many components that are interconnected, and this component, in order to provide the output, should first read all the input, yeah? And now, in case I will start all of them once, that means this will start this. So, in the first execution, this component will not be ready to provide output. But why? Because the component, this one, it's not in the first iteration, didn't provide the output. So the input that will this will take will not be still valid. So we need to have a kind of provider consumer principle. So in order to consume, we first need to provide. In this case, we don't have to start the C1 until the C3 did not provide any information. So we will need to stop a little C3 from C1 from execution until the C3 will not execute. It is not depending anymore from everyone. And the C4 will execute only if this and this is. So in our case, we should somehow provide the flow of the information. So first should be activated this one. After that, we can evaluate this one. After that, we can evaluate this one. And only the last, the C4 will be ready to take all the information from all the system. Yeah. In this case, we should say, okay, let's start. We will put some offset in starting execution. So this component or this task, let's say 1, task 2, task 3, task 4, they should somehow start. First should start the task, okay, the task 3, yeah, the component 3. After that, the task 1, the task 2, after that 4. In this order. So we should somehow define how we can order the starting execution. More than it, most probably this one will need many iterations in order to prepare the information. Let's say it's not because of the speed of the execution, but most probably we will need to confirm that the button is pressed. We will need to have to check it 3 times, yeah. And now from the 3 times, at least we'll have an arbitration if 2 from 3, yeah. If 2 from 3 is showing a value, that means this is the real value, yeah. Okay. In this case, we will exclude the situation when we have just some noises. Okay, we'll need some filtering. In this case, we'll need more time, not only 1 millisecond, maybe few milliseconds. In this case, we'll say that the C3 should be the fastest. Okay, and usually the speed of the provider should be higher and equal than speed of the consumer. Yeah, and here we'll see. Okay, we'll say that the task free, the first one, will have 1 millisecond. Second one will be a little slower. Yeah, the 2 milliseconds. And let's say the task 2 will be little slower, and this, the fifth, will be even slower because, okay, I will see and I need to update once in 5 milliseconds. Okay, it's not so slow, but slower than others. What that means. But now let's see this offset. The second will start only after one recurrency of the first task. Yeah. After that, the second offset will have after both tasks, let's say, will start, and so on. So in this case, the last task will be ready to use the information provided by others only after 6 milliseconds. Yeah. So we have two parameters: how often it's invoked or is executed, and the order, how to start those applications in order to have the right estimation of the output. Okay, this is more or less complicated, but we will see this by the next. How we can make a task slower? Very easy. We just put a kind of alarm and provide, let's say, a recurrency. Yeah. And now we will have here a kind of countdown of this recurrency, and on the moment when it will, let's say, it will be equal to 0, that means, oh, alarm, start it. Okay, start the task A, refresh or reload the value of the next starting. Yeah, and always when we will enter here, we will count down. We'll see, okay, it's equal to 0. No, okay, in our case, yeah. So if this is higher than 0, then go here. Here is true, let's say. This is false, sorry. Yeah, it's higher than 0, yes, decrement it. Next time, higher than 0, yes, decrement it. It's higher than 0, no, it's equal to 0. Start the task. So in this case, we make some arbitrary or random recurrency, or let's say a specific recurrency. Yeah, and for the task A, let's say we will put the recurrency for 3 milliseconds. That means once from the free execution of the timer, the task A will be executed. The task B, in our case, once in a 2 milliseconds. And the task C will be once in the 4 milliseconds. Why? Because first time it will enter, it will be 4, after that 3, 2, 1, 0. 3, 2, 1, 0. 3, 2, 1, 0. Yeah, and once from 4, it will start the, it will execute. Okay, we have a short mistake because we'll need this decrement to transfer to the operation to have a kind of minus, like it is here. Yeah, but for to demonstrate the logic, I take it out from here, put here the decrement. Yeah? So now this mechanism, it's slowing down the recurrency or the recurrency of the execution of a task. Just put an alarm, and when it will, the alarm will be, let's say, the alarm counter will be equal to 0, then the task will evolve. Now we solve the problem with the recurrency. We know how to slow down the task, but how to manage the order? Very easy. The first time we init the let's clear the screen. Yeah, first time we init the value of the counter with the offset. So first time it will delay the first execution. After that, let's see. First time it will use the offset of the A. That means first time it will be delayed. After that, it will start. Yeah. So first time the offset orders the recurrency value. And we have here the recurrency value, and here we have the offset value. So this is how we proceed. Now let's see how it is working on real, and let's have an exercise to schedule, to map, to distribute the task execution. So the first one, as you remember here, yeah, we have here something like execution. All the tasks always are running, but I don't need so often. Yeah, and I try to distribute it in time. So now, first of all, in case I will apply, let's say, the recurrency, I'll see that this recurrency will be 1, 2, 3. So this one will have the red one will have recurrency is equal to 3. For the green one, 1, 2. The recurrency will be 2. For this one is 1, 2, 3, 4, 4. Yeah. So the recurrency for the blue will be once in 4 times. Yeah. Yes, and we see what we see here. Then we'll see that here we have 60% CPU load. Here we have 0%. Here we have 20%. Here we have 20%. Here we have another 20%. So only configuring the recurrency, we can save the time. Okay, 0, now 20, and medium it will have about the how many times? 20. Okay, here we have 40, about the 30% recurrency. Yeah. Why? Because somehow, and we see that one here we have twice, here we have rising of the recurrency, but we can do something like this. Let's see, this is 0. Why to not, let's say, move one of them here? Yeah, and in this case, what we will have? Yeah, let's see. In this image, we move the first execution. This is offset is equal to 1, 2, 3. Yeah, and the recurrency is 1, 2, 3. Recurrency is 3. Here we have the offset is 1, and the recurrency is 1, 2, 3, 4. So here is the offset is 0, and the recurrency is 1, 2, 1, 2. Yeah? 2. So for the blue, we'll have, let's say, okay. Anyway, we have here, yes, offset 3, recurrency 3. Offset 1, recurrency 4. Offset 0, recurrency 2. And we can see that we can even plan the execution in order to have the lowest possible CPU load, in order to not have, let's say, overflow of the system tick. Yeah. So here we'll have about, also we'll have, let's say, 20%, 20, 20, 20, 20, 20. Sometimes we have, as in this case, we'll have about 20%. 100% of the CPU load because we distributed everything in a planned way. Yeah. So now just please provide me some feedback about the this kind of multitasking using recurrency and order. How we order and how we are doing this recurrent. Yeah. Meanwhile, I'll do some comment. The difference between recurrency and order. In order to provide the order, we initiate first time with the initial value, but after that we use the recurrency. But here we have a kind of alarm once in, and we slow down by this system. So now we can run tasks at different time, different frequency, and different order, and we can say that okay, the task A should provide the information task B, so we have to ensure that task A is starting first, only after we have the task B, and so on. So in this case, we have a kind of non-preemptive operating system or sequential operating system. So anyway, as I remember, we have a kind of, in the automotive industry, it's used very often. And if you want more information, try to search for time OSEC. Yeah, and you will have a framework and your solution for that. But this kind of operating system we can write by our own, and we'll see this is very light operating system that you can write by your own. Let's say in 1 hour, that we will demonstrate, of course, in one of the next practice session. So this is all for this meeting. Now, let's say I would need some provide me some information regarding the level of understanding, the general understanding and interest. So I need this feedback from you, and I will see. This will be a kind of my mark, how I transferred you the information that I wanted to put in this. So starting from this point, you can, let's say, what is important. Let's see to this robot. We can say have a lot of components, and we can define for everyone a single task, put the recurrency and ordering it, and we will have a very low CPU load. But in case we will use this approach only in the loop, we'll have trouble with the CPU load, and more than it, will have other problems. So now we are defining a multitasking by using sequential operating system. Yeah, but the main problem, just be reminded, don't use the while instruction inside your C code ever. Doesn't matter. This is forbidden. This is a forbidden instruction in embedded systems. So others, please, I need your marks. Meanwhile, you'll have, of course, to fill the form. And okay. Thank you then for the participating, and see you the next time.